On June 3, 1998, one of the most advanced high-speed trains in the world, a symbol of German engineering, suffered a catastrophic failure. It became the country's worst ever rail disaster. So how did a simple quest for a smoother, quieter ride lead to such a horrific cascade of errors? Let's dig into how it all went so terribly wrong.
Just imagine this for a second. You're on a trip with your family, maybe enjoying a coffee, watching the world fly by at incredible speed, and then, in a blink of an eye, your whole world is torn apart. This quote captures that terrifying first moment of the Eschede disaster, a moment that was, tragically, just the beginning.
So, let's set the scene. It's just before 11 in the morning. The Intercity Express 884, or ICE 884, is rocketing from Munich to Hamburg. This train is the pride of the fleet, but inside one of its carriages, chaos is about to break loose.
George Dittman and his family are in the very first passenger car, Coach 1, when it happens. There's a violent jolt, and then this jagged piece of metal just explodes through the floor. It misses them by inches, but the danger is terrifyingly real. Something is critically, fundamentally wrong with their train.
Dittman, to his credit, acts immediately. He gets his wife and son into the next compartment, then he sprints down the train trying to find the conductor. And you have to remember, all this is happening while the train is still hurtling along at 200 kilometers per hour. But in a fateful twist, the conductor, just following the rules, insists on seeing the damage himself before he can even think about pulling the emergency brake.
So how could this happen? How can one single piece of broken metal spiral into a national tragedy? Well, to get that, we have to go back in time, because this failure wasn't a sudden event, it was actually the tragic result of a design choice made years earlier, all in the name of a quieter, more comfortable ride.
You have to understand, these ICE trains were the absolute pinnacle of rail travel. Fast, sleek, sophisticated. But they had this one nagging complaint: vibrations. At top speeds, the rattling in the dining car was so bad it just didn't feel luxurious. So the engineers were given a task: find a way to make the ride smoother.
Okay, so originally, the trains used what's called a monoblock wheel. It's exactly what it sounds like, one solid forged piece of steel. Incredibly strong, super reliable, but yeah, they could develop little flat spots that caused those annoying vibrations. The new solution was the resilient wheel. This design had a steel tire on the outside separated from the inner wheel by a 20mm rubber dampener. It gave a beautifully smooth ride, but it also introduced a new, and as it turns out, fatal weakness.
And this gets us to the science behind the failure: metal fatigue. Now get this, that thin steel tire on the outside of the wheel was constantly flexing and deforming with every single rotation. We're talking over 500,000 times a day. And each one of those cycles was creating tiny, invisible cracks that just got bigger and bigger with every single kilometer.
Now here's the part that is just unbelievable. This resilient wheel design, it was originally meant for city trams, the kind that travel at maybe 30 kilometers an hour. But it was adapted for these high-speed trains hitting 250 kilometers per hour without nearly enough testing to see how it would hold up under that kind of incredible stress. It was a catastrophic miscalculation.
Okay, so now let's go back to those final seconds before the crash. The conductor is still on his way to see the damage in Coach 1. The train is approaching the small town of Eschede, and that damaged wheel is about to set off a devastating, lightning-fast chain reaction. So that broken piece of the wheel rim, the part that shot through the floor, is now dragging along the track. For 21 seconds it scrapes along, and then it snags a track switch, a point where the track split. That instantly flips the switch, which sends the rear wheels of Coach 3 onto a totally different track. The whole car is thrown sideways and it slams directly into the concrete pier of a massive road bridge.
The impact just shears the bridge support right off. The cars behind Coach 3, well, they have nowhere to go. They just pile into the wreckage and the collapsing bridge, folding up like accordions. The force is unimaginable. 2 of the carriages are crushed by the 300-ton bridge as it comes down, flattened to a height of just 6 inches.
101 people lost their lives that day. 2 were railway workers on the ground, the rest were passengers and crew whose journeys ended in an instant.
And on top of those fatalities, 88 people were left with severe, life-altering injuries. The only reason anyone at the front of the train survived, including George Dittman and his family, was that their cars had already passed the switch and the bridge before the derailment even started. The driver of the train had no idea what had happened for another 3 kilometers. In the aftermath, as the entire country was reeling from the shock, investigators had this monumental task of figuring out what on earth went wrong. And the answer they found? Well, it was a story of systemic failure and so many ignored warnings.
You know, the first big breakthrough was finding that very piece of steel that had terrified the Dittman family. Finding it right there, lodged in the floor of the first passenger car, allowed investigators to trace the failure all the way back to one specific wheel on that one specific car.
But here's the thing. This was not some freak accident. It was predictable. As early as 1992, a well-respected research institute had warned about the potential dangers of using these wheels at high speeds. Just a year before the crash, the Hanover Tram Company, using the same wheel design, found fatigue cracks and reported it. And maybe the most damning part? The very wheel that failed had been flagged by technicians 8 separate times for making noise, but it was never taken out of service.
So you might be asking, couldn't they just check for these cracks? Well, yes, the technology existed. They were machines that could detect these microscopic flaws. But the railway company chose not to use them, complaining that they produced too many false alarms. Instead, they relied on technicians with flashlights, a method completely incapable of spotting the tiny cracks of metal fatigue before they become deadly.
And this right here, this is the tragic, heartbreaking irony at the center of this whole disaster. That rubber ring, the very part that was added to get rid of vibrations and make the ride more comfortable, it did its job too well. It completely masked the telltale rumbles and noises that would have screamed to the maintenance crews that the wheel was failing. In the search for a quiet ride, they had silenced a critical warning sign.
You know, a disaster of this scale forces a complete re-evaluation of everything. The lessons that were learned from the wreckage at Eschede fundamentally changed railway engineering, not just in Germany, but really all around the world. The changes were swift and they were sweeping. All of those resilient wheels were immediately ripped out and replaced with the old, reliable monoblock design. To stop a crash like this from ever happening again, bridges near sensitive track switches were totally redesigned. Even the windows, which had tragically trapped people inside the wreckage, were replaced. And today, the Eschede disaster is required reading for every new railway engineer in Germany.
And that really brings us to the ultimate takeaway here. That problem that the engineers tried so hard to solve, those annoying vibrations, it was never really a flaw. It was data. It was the system telling you that something was wearing down and needed a look. By silencing that signal, they basically made the entire system blind to its own oncoming failure.
The story of Eschede leaves us with a really critical question, and it applies to so much more than just trains. It forces us to ask ourselves, where do we draw the line between progress and protection? And it's a stark reminder that sometimes the most important features of any system are the little noises and vibrations that tell us when something is about to break.